Hi, my name is Manoj Tulasidas. I'm an associate professor of computer science in the education track at Singapore Management University. My paper is a recommendation on how to teach K-means in introductory analytics courses. We will start with the problem statement. K-means clustering doesn't offer a clear metric for case selection. The motivation behind this paper will be a survey of all the existing metrics out there to select the best one for case selection. So the state of art will be the existing metrics. There are some internal metrics that come out of K-means clustering algorithm, and there are some classic metrics. So we will list them and we will study them in some detail. In addition to those metrics, we also have algorithms that are designed to automatically zoom in on the right number of clusters to form. The key idea behind this work is a method by which we can compare various metrics and algorithms, because two different metrics might tell you the right number of clusters to form. So how do you know one is better than the other? So in that context, we will define a metric called gamma based on the curvature of the peak, and we will study the performance of the various metrics on synthetic as well as real data, based on which we will decide on the best metric to use and teach in our courses. So the performance of the various metrics on simulated and real data will be the tests that are conducted. In teaching VRC to our students, we are able to connect the definition and the mathematics behind it to their existing knowledge, which is a very satisfying situation both for the teachers as well as the students. K-means clustering from a pedagogical perspective has a lot going for it. It is perhaps the first unsupervised algorithm that you learn and that you teach, because it's conceptually simple, it's easy to explain and easy to understand, and it is very well established, so it is well implemented in all sorts of machine learning and statistical packages. The problem is really that it doesn't have a good quality measure that comes out of the algorithm directly. So we cannot decide on the right number of clusters to form. What we end up doing and teaching is this subjective elbow method on the sum of square errors, which, being subjective, cannot be automated. So the motivation behind this work is to survey the existing metrics and pick out the one that might be best amenable to automation and also has good pedagogical properties. Looking at the state of the art, there are internal metrics like sum of square errors that come out of K-means clustering. But as you know, sum of square errors is scale dependent. In order to address the question of scale dependency, maybe we can think of using the coefficient of determination, which is the ratio of the variance explained by your model. So it's a ratio, no scale dependence, but it also doesn't have any clear peak. So as you increase the number of clusters to the maximum number, which is the number of observations, as k tends to n, r square will tend to 1 and SSE will tend to 0, implying that those are the perfect models, but they clearly are not. The variance ratio criterion is the ratio of the between and within sums of squares divided by appropriate factors to account for the degrees of freedom. There are information criteria like AIC, Akai-K information criteria, and Bayesian information criteria. They are designed to penalize overfitting, and they are based on a maximum likelihood. Then there are various other criteria like silhouette width, Davies-Bouldin index, and gap statistics, and an evaluation function called f of k. All these metrics are described in the paper and compared. In addition to these classic metrics, we have certain algorithms that are designed to solve the case selection problem. PG means projected Gaussian is a way in which you project both the data and the model, the clusters, into a linear space and then study the variance. X means is a way in which you can address the scalability issues of K-means. There are J-means and combined index, etc. None of them actually generate a quality metric that is easily taught at undergraduate introductory levels. The one that seems to do best seems to be VRC, the Variance Ratio Criterion. It has good properties because the right K would be a maximum in that distribution of a VRC, which is easy to find automatically. Secondly, it is easy to connect that to SSE and R square, and that is good from a pedagogical perspective. In order to perform the tests on these various metrics, we generate data, synthetic data, simulated data, using the cluster generation package in R, using parameters, the number of clusters running from 5 to 20, and a number of variables running from 2 to 32. And then there is a separation index called J star. When it is high, the clusters are well separated. When it is low, like 0.01, then the clusters are expected to be realistic. Other hyperparameters include the number of noisy variables, outliers, etc., which we set to 0, cluster membership, constant, and the range of variance 1 to 10. And in addition to synthetic data, we use real data sets, the standard ones, iris, wine, and seeds from UCI, as well as another one that is a locally collected data, young adult data set collected from my students, 127 of them in 2 classes because male and female students, height, weight, hair length, and age. Height and weight, obviously girls tend to be lighter and shorter than boys. Length of hair, girls tend to have longer hair, so there are distinguishing features in these 3 variables. Age also is an interesting feature in Singapore because boys tend to have done their military service and therefore they're slightly older than girls in our classes. To illustrate the J star, the separation index in synthetic data, if you set it to high, like 34%, you get well separated clusters, and if you set it to 0.01, 1%, then it is realistic kind of clusters. So comparing VRC to other metrics, the problem that you have is that we might get different metrics giving us the right number of clusters as the generated one. So how do you know which one is better? So we looked at the curvature. In a continuous function, curvature is defined as a second derivative, or is proportional to the second derivative. In a 3-point measurement, that is what you have, and that can be translated to a discrete case, and it was called gamma in our paper, coming from mathematical finance. So gamma is actually a dimensionless entity proportional to the second derivative at the peak. If gamma is high, that means the peak is well defined. In order to illustrate that further, if you look at the gamma of a normal distribution where the standard deviation is running from 0 to 2, we can see that as the standard deviation sigma gets closer to 0, gamma shoots up. Notice that the y-axis is actually logarithmic, so gamma does have information about how sharp the peak is. Now, looking at the synthetic data first, where we have the number of generated clusters, and we're trying to see the fraction of the times different metrics detect the right number of clusters. Turns out that VRC does it 100% of the time when clusters are well separated, and about 60% of the time in realistic clusters. Davies-Bouldin does fairly well in realistic clusters, easily comparable to VRC. But Davies-Bouldin has this problem that it's not easy to describe it to our undergraduate students. Pictorially, this is what it looks like. Elbow method is in the top row, so we're looking for an elbow as we increase k in SSC distribution. We can clearly see the elbows in most of these distributions, except the last column where both the elbow method and the VRC method actually fail. When we go to the real data, we assume that the number of classes we have should be the right number of clusters. So for iris data, we have 3 species of flowers, so the number of clusters should be 3, young adult, male and female, 2 classes. Wine is supposed to be 3, seeds supposed to be 3 also. VRC seems to do quite well for young adult, wine and seeds, and Davies-Bouldin is not very good, but GAP seems to do well for iris, young adult, and seeds, but it's not easy to quantify the significance of the measurement because GAP doesn't do it using a minimum or maximum, so there is no curvature to actually look at. And besides that, GAP is prohibitively expensive in terms of computational time. Looking at the significance of the peak gamma value, VRC is better than Davies-Bouldin for both young adult and wine. And in the case of seeds, obviously VRC succeeds in getting the number 3 while Davies-Bouldin fails. And this is a comparison in terms of the distribution. We can see VRC in purple line with purple points. Davies-Bouldin is in a red dashed line with red dots, and the elbow method is in blue. Clearly, elbow method is hard to automate because we have to decide, looking at the shape, where the elbow is. Coming to the concluding part, the key pedagogical concepts that we are able to teach using VRC would be the connections between various statistical entities like R square, SST, SSC in the definition of VRC. It is shown in the paper, and the concept of degrees of freedom also can be taught using VRC. Another one, which I did not mention in the presentation due to time constraints, is the limitation of the algorithms. The implicit assumptions in k-means that it will work best for spherical clusters that are roughly uniform in terms of membership and variance. That can be highlighted, and also the feature selection methods using purity if the data is labeled, that can be discussed also. Simulation is an important tool, can be introduced in this topic. Finally, the concept of automated generation of insights, which is the gold standard for data analytics, that can be illustrated and reinforced. To wrap it up, VRC is a clear winner, followed closely by Davis-Bouldin. So VRC wins out both in the synthetic data and real data, and it can easily replace the subjective ELPO method. Among the other metrics, GAP seems to be fairly good, but it is computationally very expensive, and there is no way to quantify the significance. We cannot compute gamma because it doesn't determine the right number of clusters using a maximum or a minimum. AIC and BIC, these information criteria, perform very poorly, and maybe it is best not to teach it in our classes. One point to highlight is the fact that VRC can be automated and it can be used in the deployment of k-means clustering in unattended situations. So that would be a future direction for this work, to figure out an unattended recursive kind of k-means clustering algorithm. That brings us to the end of this talk, and my email address is there. You can contact me if you have any questions, or if you're bored with all these things, you can go to that website manoj.sg/uu, where you will be treated to a very nice video on something that is completely unrelated. Thank you very much.